Hello, everyone. Welcome to this conference day. I'm going to talk about Makepad. This is our project, our startup, and we're trying to build a UI stack in Rust. And a very long time ago, when I was building a web-based IDE called Cloud9 IDE, we also built a code editor called ACE. It was based on HTML. And it used divs to render all the text in the code editor, and a virtual viewport, of course, because otherwise you couldn't update it fast enough. And I was struck by how tedious and how stupid it is to try to abuse an HTML render engine for anything other than Wikipedia, essentially. Because it was always in our way. We had designers making the UI designs, and then we had a bunch of programmers who were like, yeah, really? We're already so behind, and you keep adding new UI. We can't process fast enough. So we had a huge bottleneck in our application development. Besides things being so hard that apparently we were one of the 2 companies in the world that were making a text editor in a browser. So that was madness. At the time, we thought it was all right, but I learned that I couldn't do anything. I couldn't innovate the editor because I wanted to do inline widgets. I wanted to do fancy text editing that uses a lot of UI mingled in with the editor. And in a browser, I couldn't do it. One of the things I wanted to do was animated code folding. Simple thing, you think. Computers have been faster than a Commodore 64 for a while, but in HTML you can't do it. And it's also very hard to control because you deploy on different browsers, and Safari breaks something again, and it is just tedious. So after that startup, I thought, well, let's start over. Let's start from scratch with WebGL. That was just out at the time. You have Shader Toy. You can see that the GPU is programmable. Shaders are little programs that run on your GPU, not your CPU. And you can use them to transform geometry, or you can use them to style pixels. Essentially, you write functional little programs that run on pixels. And let's see if I can, hold on. There we go. So this was my Makepad JavaScript peak, essentially. This was where I got. So all of this is live coding JavaScript, and this is actually the only structural JavaScript editor that I've ever seen existing. This is essentially an array that has 2 formatting modes. As you type, everything is live formatted. So when you, for instance, I right-align the objects to the key in the object. It's a feature that is actually very hard to do if you don't have a structure editor that formats as you type. And this is where I had the first idea of writing shaders using the host language, or something that looks like the syntax of the host language. In this case, it's JavaScript. However, I was like, okay, you can live edit everything. Everything works. The problem is the performance is just not there if you want to do something complicated. And I had a friend of mine in game development, and he said, like, cool, you made a UI kit. For what exactly? I was like, okay. Yeah, you can't get data into the browser because it's going to just barf on it, or large amounts of data. And it's also very unstable. Like every time I ran these web-based demos, or you had to restart the browser after a few hours or something. It was always, and if you live code in this thing for half an hour at the time, it would just crash Chrome with garbage collector segfault or something. It was really great because as a developer, you can't do anything about it. You don't have to reach into the platform. You fly in a ticket into the Chrome thing and then hope that somehow it'll get fixed, unless you want to do that yourself, which I did not. So at the time I was like, okay, so maybe it's not just HTML, maybe JavaScript is also the problem. And along came Rust. I spread out over years. But so Eddie, who worked at Mozilla at the time, is my co-founder. If you have any questions later, Eddie, stand up. So I was like, okay, what about this idea of writing a hybridized shader UI, but now let's try to do it in Rust, right? And Rust is fast, very, very fast. I could finally do these things that are not so great in JavaScript, like, for instance, this is a fractal zoomer running in F64, so 64-bit float. And it's using a worker pool with just tiles, just like Google Maps, essentially. It does the tile tweening on the GPU. By the way, if the frame rate hiccups, that's not me. It's the Beamer has a frame buffer in between that is just like messing things up. So I have like smooth 120 hertz here, and you have, I don't know what that is. But anyway, so just so you know, it does run 120 hertz smoothly. And also for UI. So someone in finance was like, can you draw a lot of number markers? And I'm like, yeah. Okay, let's do it. And I was like, okay, let's just update it every frame. They're supposed to be red and green, but they're sort of mixed in between. This is also running 120 hertz. You can actually update the screen again, unlike in a web browser with HTML. So let me get back to our original goal. That I had with building IDEs is that I want to unify programming and design again. Like we had in Visual Basic, I mean, it wasn't much design. You could design a UI, but it was designed for the time. And IDE used to mean that it was a collection of tools. You know, not just a debugger and a code editor. There was a UI designer, icon editor, all these things that were lost to us, essentially, as we moved towards web or other platforms. And so the design goal is that we have a code editor and we have a design tool, and they're stuck on the same code, essentially. So when you move something in the design tool, it updates the code editor in reverse. This is a work in progress. Like we're currently building the Visual Designer. We've built the entire UI stack, platform abstractions. Code editors on the way now, the final code editor. I think it's the third code editor that we've written. But because the code editors, doing code editors extendably is actually quite a hard problem. Either way, we decided to build a test UI. This is our test UI. It's a synthesizer. It also plays sound. And then you can, it has all the little bits and bobs in the UI. It's really kind of a fun thing. It's a small synthesizer that a friend of mine has a, this is not rocket science company, he's making synthesizers. He's just like, let's build you a demo synthesizer, and on a few afternoons he programmed the synthesizer that's now also MIT in our code base. But so this is like a fully fledged UI. It's got little graphs. You have a sequencer and a little piano. So the keys on this piano are all pixel shaders. So when you move the mouse, an actual virtual lamp moves straight up over the key so that it shines, and then it moves back down again. You know, you don't fake this with gradients. You can actually do something here that looks nice. Well, as you can see, the preset editor is a work in progress because this required us to really do some design on the APIs, which I will talk about in a bit. And we also made a mobile UI, which I think will it work? It's the same sequencer. Let's see if I can play. And hold on. This is the same UI, or essentially these are multiple UIs running on the same Rust code. Our UI language is a DSL, that is a subset of that is tokenized in the Rust tokenizer, just like a macro, but it has a different syntax. And one of the things you can do is you can create multiple UIs that bind to the same state. So here you see that when I draw stuff on the thing on the right, it's data bound to the stuff on the left. And this is a way of programming multi-device UIs, essentially. There used to be the responsive thing where you scale something and then images move, but I find that that only really works for pizza ordering apps maybe, or something very, very basic where images can just shift around. But normally when you make a mobile app, you really want to focus on mobile UX. It's not a mouse, it doesn't have a keyboard, it is touch, and it changes the UI. So what you do is you just make multiple UIs and have only one on-click handler, but I'll show that in a bit. And of course, we're finally moving towards our final goal, and that is that the UI is visually designable. So over here you see essentially the outline. This is very similar to what would be your outline in Figma. The font size and the style of this is of course not good. But here you see the desktop app with all the little frames. And here is the component view, essentially. So this UI is built out of components that are inherited. I'll go into that when I talk about the language more. But essentially, you can design a component and then instance that as many times as you want, overriding subproperties. It is very similar to how CSS composes, except it's linear inheritance. So here we have the Visual Designer, the first prototype of it, where the component model of the whole application is splattered out. Let's see. Yeah, so to do these kinds of UIs, this is just a test of UI. The other UIs that we test are IDEs, code editors, and essentially advanced UIs that were really hard to write in other systems. The idea is that it's live editable. Rust is a compiled language, but if you put a block in the Rust file that is a different language, you can also ask the application to hot patch it. So that I cannot demo yet. We're working on that. The design tool manipulates text in the code editor, so it stands on the undo stack of the code editor, which is really nice, because then you always have this dual view. You can edit text just like you would edit XML or HTML, and you can edit it visually. So these slides are essentially a Makepad app. The DSL allows you, the UI language allows you to compose applications. A few days before the talk, I was like, wait, I have a slide widget and I have a UI structure. Why can't I just cut and paste the application instances into the slides? So I just copied our examples, linked it using a crate, imported a widget in our structure, and yeah, now I could run our example application essentially inside a slide as a real application. And it was also a nice stress test, because normally this is the amount of complexity that you have in an application. You just have a single UI. But now I was like, okay, what if I do 5 of those? Or these are all separate instances of the UI. I'm not moving it around. And what's even worse, I would say, is when I scroll, I'm actually regenerating all of the UI, because I didn't optimize it with a viewport yet. And this is so great about Rust, is that you can, sometimes in these situations, you can just be really dumb and get away with it. And in JavaScript, you cannot. So this is running at 120 Hertz for essentially 10 times the UI that we use now. Then I wanted to show you some actual code to give a bit of context. So this IDE is my old IDE. When I started learning Rust 4 years ago, I was like, okay, let's build an IDE immediately. So without any knowledge of Rust, I started building it. And it took me 9 months until I had my IDE that I could use myself, which is still this thing. It is really terrible, except for this one feature that I finally got that I never managed before, which is animated code folding. And it's so fast, it also runs in a browser. This is this is the WebAssembly build of the same thing. So now, because of this feature, I can never move back to Visual Studio Code again. Because you're like, zoom! Oh no! Oh, it's like an impulse trigger, because I use it to to quickly find a function or a structure, and it doesn't fold away the content, so it keeps my spatial awareness of where I am in the code intact. So you can just jump to the middle here. So yeah, let's look a little bit at the structure that we've made for applications. In this case, we have an app RS, which is different from a main and a lib, because Makepad applications need to compile to both a dynamic library and a binary, like an executable. The reason is that some platforms, like Android or WebAssembly, essentially require you to make a DLL, or a dynamic library. So that we have like a stub, lib, and main in front of app. So that's why you can reuse it. Then you have a live design macro. This is really just essentially says, from here, it is the UI DSL, just turn it into a string. This essentially gets turned into string minus these little references here. And these are type connections between Rust and the DSL. The macro just puts a type ID of this class inside the list. So that means you can inherit, so this kind of inherits a structure from a Rust object. The Rust object is the base. This is very similar to the original architecture of SpiderMonkey in web browsers, where you would instantiate a JavaScript object with a C base class. So this is the same here. And in this case, we're looking at the slides. So let's look very briefly at the Rust object that we have. Here's app. We have the UI itself, which is a widget reference. It just holds on to the root node of your UI. And presets, it has an audio graph, which is the little audio engine that is doing the synthesizer, and it has some MIDI input. And now you can assign, here we go. Now you can assign to that UI node in the DSL a UI object. If you look at, hold on, that's an important feature part. You see I do derive live here. This is a proc macro that allows you to bind this dynamic language to Rust structs. It's essentially similar to using Serde to deserialize JSON into Rust. It's pretty much the same. You take a language, in this case it's a key value language with a bunch of features like inline shaders and inheritance, and then you just apply it to Rust. It's just a deserializer. It's not much more complicated than that. It's not a scripting language with an interpreter. It is literally a deserializer, and that's also what keeps it so simple. You can change the DSL and then just reapply it to a Rust object, and you update the state. In this case, we make a desktop window widget, and then I make a slides view widget with a bunch of slides in there. These are the slides. And then what you can do is inside a slide, you can just dump a bunch of UI. Like in this case, we dump the Mandelbrot widget, the numbers, or in this case, the synthesizer app is actually the root of this whole tree, meaning that because it has a fairly complicated piece of orchestration I'll show in a second, I just jammed a slide viewer in the root of my application. And here you spawn the desktop UI, the mobile UI. You can override some values here, like set the width. And so yeah, that's how it's composable. Let's see if I can show you the desktop app. Let's see, code folding is very useful. Frame is like my div. And you can inherit all these components from frame and then start overriding properties and putting in subnodes. It's very similar to HTML, except HTML missed this concept of inheritance. And I think that is essential to UI, because if you look at what this does, is it maps very closely to how UI designers make UIs in Figma. It is very similar. You make an instance of a design, you can override some properties, and that's it. So here's the main application at the bottom, app desktop. And you show the presets widget, then you make another frame, you make a gradient, you have scrollable containers. It is really a DSL, except that it's very easily extendable from Rust. Because that is the important part for a Rust UI framework. how easy is it to use from Rust, right? Um, because there's always been this fight between how do you make a UI that is designable and how do you make a UI that's programmable? And nobody has really solved that well, because the UIs that are nicely programmable always kind of run out at the end like, okay, well, visual designer, yeah, we tried, we couldn't really do it. Or it becomes this hellhole of CSS hacks just to even attempt it. Let's see, so data binding I'll talk about in a sec. I think what is important to see in the architecture is that we use a poll architecture. So if you have a button with an on-click handler, you can write it in a couple of ways. One of the ways is you write it using a closure on-click. Except in Rust, when you do a closure, you have to put your state into an RC ref cell or something that you can reach, which makes it extremely inconvenient when you have to do that. And so what we try to do is to make an event flow that is query-based but never actually opens a closure and keeps everything unlocked in the flow. So here I hope I can explain this clearly. So the system sends an event to the UI which is like, hey, draw yourself, yes? No, not really. I mean, I could try. Hold on. No, I broke that in my old version. This thing is 4 years old. It's terrible. I have to actually recompile my IDE to do this. Luckily, that's not really a big issue. I had it, but then I lost it. Is that better? It's so great when you can recompile your IDE, by the way. It's lovely. So we get a draw event. And then what happens is you call on this UI object, that's the root node of your UI, draw yourself, right? Draw widget. And what I did is I made the draw flow return a result as a continuation. And that means that if you call this function again after you did that, after you get a result of continuing, then the whole code flow resumes exactly where it was. And this is not a difficult thing. You just have to write your code flow with state machines to be resumable. And you only need to do that in widgets that can contain other widgets. In this case, I'm trying to draw the items in this thing. Hold on. I'm trying to draw the items in this list. Right? So if you make a widget, who owns the data? And this is a difficult question, because if you have a widget that has its own items in there, you often have to give it your data or synchronize your data. This is the way old UI systems used to do that until the functional flow systems started to say, well, you know, why don't you just regenerate the UI when you change the data, and then we'll figure it out from there. And that's exactly what this is doing. You query, in this case, it's a swipe list, and you call the multi-getter, which is a set. So you call get swipe list set. This means that you get any number of preset lists here. That's because this UI can be instanced many, many times, and you don't want to duplicate this piece of code for every instance of the UI. As you saw, you have the mobile UI, multiple instances in different slides. And then you compare if the hook item or the next item is in this set of swipe lists, and if so, you borrow it, and then you draw the items in an immediate mode. Here you see that I get an entry. You have to come up with an ID. This is very similar to React. I just decided not to bother with solving it in any different way, because there are not many solutions. Just make an ID. And then you spawn an entry item, and you use the convenience APIs to override the text label. This is very different from the template approach, where you would you would kind of inline code into a UI structure. I'm really opposed to that because I don't know how to make a design tool work with that, because as soon as you spread code throughout your design, the design tool doesn't know what to do anymore. So that's why we're very strict about that. And that's it. This is I think, not more complicated than eGUI, or not much more, but it is way more efficient. So the UI is pretty much entirely incremental, except for my slide viewer where I needed to implement some windowing. It's entirely incremental, so it scales much further than a pure immediate mode GUI, where you draw and handle events at the same time. In Makepad, drawing is a special event, and everything else is on-click, mouse move, those kinds of things. So how do you handle events, right? This is the drawing part. That's all right. So how do you handle events? Let's see if I can get an on-click here. It's always the nice. Right. So here's the panic button, which stops the synthesizer. It's a required feature in the synthesizer when some note hangs or whatever. And what you do is you get the button set, which is any number of panic buttons. They could be any number. And then you call the clicked method on it with the actions object, which contains all the events that hit a widget. And this query is extremely cheap because it caches the query result of the buttons, and then it just checks an enum to see if there is an event for the particular widget. So this is completely borrow checker unlocked. This is just an if. It doesn't do anything with your state. If you do this as a closure, as I said, you have many problems. And I think this is a really solid improvement. Also, all of these getters return a wrapped component object that is an RC ref cell to a DIN trait. And that means you can keep these things around, because the only time they get borrowed is when you call a method on it. And they can also be null. This function actually fails silently, which is, for this kind of stuff, great, because if I remove this button in the UI designer, you don't want your Rust code to crash, right? You don't want it to randomly crash when it does that. You can turn on warnings when it doesn't find it, but you don't want it to crash. So this is essentially a very rugged piece of Rust code that is using convenience wrappers around the components. And I think this is a good path here, because I think the orchestration code for the entire synthesizer, my font is now so big I can't read my line numbers. It's like 400 lines of code. It's really not that much. And so here we have the immediate mode flow, right? Here you have your data that just defines the UI, and as the data changes, you just redraw the UI and you're done. But there are also other paradigms, like data binding, for instance. Here is, if you look at all these little sliders, right? This is changing a value in the synthesizer. The synthesizer is running in another thread. It has atomics on all its fields, and if you can just bind the slider straight to a value in the synthesizer, you don't need to deal with any event handling. So what I did is I made a data binding system that allows you to bind a Rust struct, because these live things, they're essentially a form of reflection, right? I said that I could apply the DSL to this application using this trait. But that also means that I could implement data binding that way by generating a bit of dynamic UI structure and then applying that to the UI. And that's essentially what's happening here. The slider generates a little fragment of that UI DSL and then applies that to the UI, and then you have data binding. Here's the apply code. Let's see. Right, so this slider is moving that value in the graph, and you use data binding. And that means that the only place where that is stated is here. Right? Imagine how much more work it would be if you have to do event handlers and tying that together. So that's another, and I think it's a different model that works for. It's a different model that works for different use cases. Okay, how much time do I have? Lots. Okay. All right. Yeah. So the future of this is that we're going to release 0.4.0 soon. That includes all of the platforms. We've written native backends for Windows with DirectX, Linux, OpenGL right now, Mac with Metal, web with WebGL right now, WebGPU we'll add later, and we have it running on Android. And for that I wanted to do a little live compile demo. So one of the things we did with Android was, so we made a new build tool, because Makepad is going to have to build on all of these platforms, right? Like, especially WebAssembly and Android are very specific in the build tooling. So hopefully, this is in some day this will be able to be built into Cargo in some sense, because I don't think these are strange build targets. But they need to do a lot more than just generate a binary. They need to generate a package, or they need to strip a WASM build. So what we did is we made the entire Android SDK installable in one go. I'm not going to do that now because you'll have to believe me, but you can run Android toolchain install, and it will pull all the dependencies from the original Google sources, strip them all out, and turn it into, I think, 150 megabytes of tooling. That's all you need to build an Android application. And all you need to do then is you do Cargo Makepad Android, which is our Cargo plugin, and the rest of it is a normal Cargo command line. In this case, run and then a project Makepad example Ironfish, which is the slide right now. Hold on, I'm going to do a Cargo clean. I love doing Cargo cleans, but I'm going to build it. So here's the Android phone. This is a clean build of all our libraries. As you see, we don't like dependencies that we didn't make. So here we have the slides on the Android phone. So that's a solid, what is it, 9.25 seconds to. And I'll make sure that it also plays a sound. Hold on, let me. So this is a little silly trick for me to avoid putting it in a comment block. Let's see, desktop. So you have two types of properties in RDSL. One are user-named objects, which could be child components, and the other one are Rust fields. And Rust fields use a colon, and the other one use an equal sign. So that's an iteration cycle of 3 seconds, I think. That's not so bad. So we have the same synthesizer natively now on a phone. I also tried to build it for web, this whole thing, but this was a little bit of, this presentation was a little bit of, oh wait, now it's a synthesizer. Let me get my presentation back. By the way, this is my workflow because I compile on keydown with my IDE, and this is also, so when you make an error in the code, it immediately shows you, hold on. Where are my nice error underlines? Huh. Guess change, oh, I know. It's now behind the font, see? So let's see. Did I get my presentation back? Yeah. So Rust is so reliable. It's great. You know, you can just do this, recompile, and do stuff, and it doesn't bother me anymore. It just always works pretty much. Let's see. Yeah, so I tried to build this presentation for web, but because I just cloned this UI so many times, WebAssembly actually ran out of memory, and it does that very quickly. Actually, if you do it, if you use, because every one of these things is, I think, a frame buffer, because I turned on frame buffer caching, so that allocates quite a lot of RAM. And on native, it's just like I don't even notice. I didn't even notice there was a problem. But on web, it immediately starts keeling over. And that is, I'd say that is a very strong advantage of Rust, that once you make a workload that is too complicated for a browser, for a WebAssembly, or needs too much compute, needs too much threads, or having the option to drop to native is something that I've always missed as a web developer, right? So this is also why I'm really not a fan of things like Electron, because Electron is like the same shitty shit as web, except now native, which, like, why? It's like the worst of both worlds, right? So to me, that is the main value of Rust, is that we can now access all these targets, but you can actually use the compute in the target available to you. Let's see. I didn't actually time this talk very well, as you can tell. I need to...
So Rik, you can actually show the synthesizer alone on that, right? You could just show the synthesizer alone on that. That looks fine.
Oh, right. That was also in my demo. It's localhost. Oh, and I just cargo cleaned it. Oops. So I'll rebuild it quickly. So yeah, this is our work in progress. I still have to write the WebAssembly build tool. As you can see, when you do WebAssembly with threads, you have to compile the Rust standard library yourself. This is a command line flag for the compiler. So now I have 70 dependencies, which is really terrible for me. But it's not so bad. 15 seconds for a build. It's not so bad. There we go. But here we go. Oh, the frame rate is not. You cannot even see this on a projector, but here it looks crap. But see, it should be slower. Yeah, this is slower. But hey, it still works, right? It's like, come on, thing. My click area gone? Well, that's good about browsers. You can refresh them. That is definitely a good thing, because in a browser, refreshing is often used to sort of clear your crappy programming skills of state, right? Which is, but yeah, I think this also works. So this is using WebAssembly threads, and that's a really cool feature that you can use normal Rust threads directly in WebAssembly. I did a whole bunch of code for that. Oh yeah, this is also great. Like, look at that sluggish resize. Oh my god. Like, oh. As a programmer, this hurts me. This hurts me. This hurts me. So then you have this, and you're like, yeah, that's how you do it. You know, it's little things that made me hate the browser. But we're still going to run in it, and that'll be fine. But you can see, oh, I actually, last time I tried this was much worse. But yeah, it's actually did compile. And this is also where our dependency management is important, because if you try to deploy as WebAssembly in a browser, you don't want to be 10 megabytes of binary, right? Web browsers, you want to stay like, I don't know, 500 kilobytes of a WebAssembly file. I think this one broadly zipped with everything in it. Well, broadly is not zipped. Broadly compressed. We will see, I think, around 500K over the wire for this whole thing. So that's really not bad. Let's see if I can show something else. Yeah, this was so this was my first IDE in Rust. I still like it. It's also great that it runs on web. And so the live coding part, this editor part is what we're rewriting now. But this was an early prototype of how it worked. So here you see code variables, and it uses the reflection of the DSL language that we had, which is then called live body. It was different, and it was much worse. But let's see, you can use these sliders to slide these values, which is modifying values in a shader right now. So it's hot patching these values in a shader. This tree is actually 3D, sort of. And if you have a quest, you can press the goggles button and walk around the tree with the whole IDE on your hand. This is, I wanted to try to see how fast you can make a UI framework to integrate it in AR and VR environments. And it works very well because, as I said, even fairly complicated UIs like this only take milliseconds to render. If you want to run 120 Hertz, you only have 8 milliseconds. And so that it means for an average UI, like the synthesizer, we spent about 0.5 milliseconds to update the UI for everything you want. And that means you can change your mode of programming to be much more sloppy in that sense. You don't need to do everything incremental. You of course should, because battery use is a thing, but you don't need to. You don't need to anymore. Let's see. Let's see if I can show anything else. Okay, the file tree is now really, really tiny. Let's show the numbers. Yeah, let's show the piano widget. Audio graph. Piano. Yeah. So I'll show a little bit the shader programming that you need to do to draw that piano. Because to me, it's these kind of widgets that are that really benefit from having shader styling, right? If you just change the background color, you can do that with any UI system. But if you want to draw these kinds of piano keys, you want to write a little pixel shader. So in Makepad, you can draw a shader by just defining some functions that look a lot like Rust, but they're kind of not. They're semantically closer to GLSL because I have to transpile them to all these backend GPU languages. So you define a pixel function, and self, in this case, is the data I/O, or the data in from the Rust side, where you set values and you can read them directly in the shader. So for instance, in this case, you have an, here, let's see where the piano widget is, piano key, yeah. 5 minutes, okay. Good, yeah, this is good. I can explain a little bit about the shaders. So you make a struct in Rust. You derive live on it. This is the binding mapping. And as you can see, I also have an attribute called deref to do inheritance, which I know is an anti-pattern, but I don't care. It works very well for this feature. You derive the shader from drawQuad, which draws a quad on the screen, and you add some properties, like is black, pressed, hovered, focused. And then in the shader, when you inherit the object from that Rust type, you now have access to self.isBlack. So this compiles away the entire barrier between the GPU and the CPU, and that makes it much more ergonomic to do shader styling, because otherwise you'd have to, cram values in an attribute array and calculate offsets by hand. This is what compilers are supposed to do. So it's one of those things where having our own shader compiler is very convenient. And in this case, we draw an SDF shape. So this is a very funky API. It's essentially a canvas API in a pixel shader. You can do circle, circle, combine, union, all these things in a pixel shader. And what is cool about a pixel shader is, like, you can set the color of everything per pixel. So in this case, I'm drawing a box. This is a rounded corner box. And I'm using as the color a function, in this case, black key and white key. And black key is this little height map. It's like a little height map where you do a dot product and then you have a light. And the white key is simply a gradient. So here you see how in a shader you can compose different rendering essentially by just overriding a color. It is a very different experience if you can override a color per pixel than if you have to do it with the vector API, because all the browser UIs or most UI kits are essentially based on vector APIs. Let me see if I can find a little example of how you then style it. Here I use a distance field to draw a little shape, right? This is probably an icon. Let's see what this is. Oh, it's a drop down. And the same goes for text. So here you have the get color function of text. Because the shaders are inheritable, I can override methods that are called in the base class. So you can override get color. Now, because pixel in the text render is a bit complicated, it does a bunch of texture lookups and color space mappings. But here, you can still return a color per pixel. So this is a text renderer where you can define the color per pixel for anything and parameterize it directly from Rust. And this inheritance structure, I think, I have never seen before, where you can inherit shaders to do your UI styling. And I hope it catches on, because for us, our designer, Sebastian, has actually made this entire UI, including the pixel shaders, which I find very amazing, because he's not a programmer, he's a designer. But apparently it is convenient enough that, that you can write these things. So I have 2 minutes left. Does that include questions?
No.
No. Okay. Yeah, let's do that. I think so. This was I was skimming over the surface here because the surface area is very, very large for this project. We have written every single component from our own implementation, micro implementation of Serde to Eddie's popular things like your own regex engine and a WASM engine. So we're going to merge that in soon. And of course, the reason for that is that we want to minimize compile times, because the way we think Makepad will happen is that it'll become the foundation library or a foundation library to build applications. And that means that every single hello world button click thing will include our library dependencies. And right now, on my fastest Linux box, with everything cargo cleaned, I can do a clean build in 5 seconds for this entire stack. This whole synthesizer will build in 5 seconds. And I believe that with that focus on that compile time, we can sort of make things lightweight again. Rust is not known for its lightweightness, or especially not with a lot of dependencies. And if you go to UI, you very quickly hit the 400 or so dependency range. And I don't find that a very pleasant experience if I accidentally type cargo clean or have to have a new Rust nightly. And also not CI. CI is going to clog you every single time. You have to wait for half an hour because these are usually very small 2-core machines. So yeah, we err on the side of not invented here. Also makes it fun to do because we get to build lots of stuff. But otherwise, that also means that what I could talk about here is extremely wide in terms of concepts. Yeah, I think I'm done.
Oh, thank you very much, Rik. Well, we got time for questions, and we got one of these. We got a catch box, so there we go.
What is the current state of accessibility support, thinking screen readers?
So I'm of two minds here. First of all, accessibility is an extremely complicated problem because of, if you look at the specification, there's like more classifications of objects than I can even remember. And I have the feeling that by the time I'm done implementing half of it, AI is going to be the screen reader. It is a little bit, yeah, we can completely do it. It's a tree, a memory. I can make an accessor for it, or I can spawn a shadow DOM. I haven't done that yet, but yeah, I have this feeling that by the time it might be important, you can just ask an AI to do it for you. It could be that it's computationally too expensive, right? Because you're going to need to run a pretty hefty GPU full blast probably to assist you. So there's that consideration, but it's definitely possible. I just haven't worked on that yet, except for reading specs and trying to get a handle on what to do.
Excellent. Oh God, more questions. Okay, we're gonna do 3 questions. So the 3 people that raised their hand, we're gonna do those because otherwise we're gonna totally run out of time. Now I'm gonna throw this thing, which is gonna be totally awful. I can't believe it.
What about iOS?
iOS. Well, I wrote this. This thing is running on Metal on all of the native Apple APIs directly. So I kind of prepared iOS. iOS should really only be a little bit of NS something or other implementations, because I looked at how it's implemented for some other abstractions, and yeah, it's not hard. But the Android stack was definitely a lot more work because we had to get on there. We have support for Apple, and under Linux we have Android. We also have direct rendering. I wanted to run it on a Raspberry Pi full screen to see how many frames per second I got, and I only got it to like 30, and when you only moved your mouse you could get 60. The Raspberry Pi is a really dreadful device to feel good about rendering about, because if you clear the screen twice you run out of memory bandwidth.
In short, we're going to support it.
It runs on the Raspberry Pi in full screen in direct rendering. And X11, we don't have Wayland right now, web and Windows. Oh yeah, I also wrote a Windows RS stripping tool because it's 3 million lines of Rust, which is not in line with my compile times. But if you strip it, I think the whole dependency stack for Makepad is only 20,000 lines of that library. So.
Can you pass the mic back there? Or just throw it to the back row and then pass it further up until we're... Or do it in one go. Oh, nice. Woo!
So I was curious about the Android.
Yeah, you have to talk into the thing, yeah.
Does this work? Ah, nice. I was curious about the Android tool you were talking about, where you like strip out the SDK.
Yeah.
Is this like, can you use it with different tools? I use Cargo APK, and I hate having this big Android SDK on my computer.
So it is a very dumb thing. It's essentially a shell script that I turned into Rust to download and strip hold on, tools, cargo, source, Android, SDK. So essentially, it's just all the paths for all the different platforms to the Android tools, and then it's a bunch of unzipping. And I have here, yeah, this is the list of files. So I binary intersected the SDK. So I essentially deleted half of the SDK and tried to compile my Android app until it stopped working, and then put it back and just split the other half. And if you do that, actually, you're only left with a few files, I think 38 in total, that you need to extract from the SDK and put in a directory. And then you can just call it, like, let's see here, compile, where you do, come on.
If your question is actually how do I build my Rust application, just shell commands, start to be later.
Yeah,
Nice.
so this is this script is designed to compile the Makepad application, including the resources, and contain them in the APK. If you're just doing a DLL, you can just steal the few build commands that are in here to do it.
Awesome.
All
Thank
right. So the next question was next to you, right? Yeah, awesome. So that is the last question. Thank you.
How's support for drag and dropping between Windows and clipboard?
Well, that guy started on it and never finished it.
Yeah, it turns out I got some other stuff to do. So
He has other stuff to do.
it's not finished yet.
This is also where open source is nice, right? Like the code base is really not that daunting. I think it is. First of all, it's Rust, so that means that it is not nearly as scary as someone's dialect of C++. And also, there's a lot of platforms. So we are open for assistance in these kinds of areas where you're like, okay, I'll implement drag and drop for Windows or for X11. X11 is the party. That is really fun system to build. Oh my. Yeah, it's like archaeology into.
All right. Thank you very much, and give a big round of applause for Rik Arends.